there, so I don't need this one. That's now I have it, and if I stop mirroring and choose it as the main display, then I don't have it for some reason.
I think the one that worked is this.
Now this is now fine. Yeah. Okay. Yeah. Okay. I can start.
You can start and hit this first.
Okay. Is the mic on?
Yes.
Okay. Yes.
You can start.
Yep. Okay. Okay. Hi all. Am I audible at the back? Okay. So my name is Agriya Khetapal, and I'm going to be speaking about enhancing the scientific Python ecosystem's interoperability with Pyodide. And so I hereby agree to abide by the Pycon APAC code of conduct and consent to being recorded and streamed. So with this, I can start. And also, I have the slides if anyone wants to follow along with my presentation. So, I'll start with my talk. So there are a few terms here which are slightly like wordy. For example, interoperability and also Pyodide, which people may not be aware of. So this is some information about me. I'm 22 years old, graduated just this August. I have a background in computer science and applied math. I'm a software engineer at Quantsite, and I contribute to the scientific Python and the Pyodide ecosystems. As for other work, I also help maintain. I've recently started helping maintain this package called Autograd that is used for forward and reverse mode automatic differentiation of NumPy code, and also the PyBAM ecosystem, which is a package and a library for mathematical modeling of batteries. I'm interested in a lot of things from Python packaging to scientific computing, compilers, and documentation, and so much more. So as for the outline of these things, I'll give a brief introduction about what Pyodide is, and then explain what I've been doing over the past year. And then you will get to know some information, some things about the Pyodide build system, and then how you can use Pyodide for your own projects. So with the first section, I would like to point out that there are a lot of Python implementations out there in the wild. CPython is the most widely used one and the reference implementation for the Python programming language that's available. But there are other implementations as well, not just CPython that you regularly use. For example, you have PyPy, Jython, GraalPy, you have IronPython, Brython, and then MicroPython, and so many more implementations. But there's also Pyodide, which is like the centerpiece of my talk. Pyodide is CPython, which is cross-compiled using the Inscription toolchain to run inside a WebAssembly-based environment. So this is, I just want to clear some things, and that is that it's an entire distribution in itself and not just an implementation. It's rather than just an implementation. So it runs on all browsers, for example, Chromium derivatives and Google Chrome, Firefox, Safari, even on Android and iOS. and in JavaScript runtimes that are common for web development, such as Node.js and Bun and Dino. So it subscribes to the write once, run anywhere paradigm. So you have Python and WebAssembly, and then you can use WebAssembly code to run Python inside the web browser. So as for what WebAssembly and Emscripten is, so this is a short recap for those who are already aware of it, and a gentle introduction to those who are not aware of it. So WebAssembly is a binary format for a stack-based virtual machine. It's intended as a compilation target for compiler backends. So it doesn't, it's not like conventional build targets that you have, for example, for Linux or macOS. So it's inherently designed to be secure and to run in constrained environments. With constrained environments, I mean a web browser where security is uh, of prime importance. So it's supported by most modern web browsers at this point in 2024. And as for Emscripten, it's a compiler toolchain that compiles C or C++ code to WebAssembly using the LLVM compiler infrastructure. And so it provides an entire toolchain from this, including the compiler, the linker, and all build utilities associated with this. So you can use EMCC as a drop-in replacement for GCC if you want to compile C or C++ code to WebAssembly. With all this, Pyodide is not yet Java. So we are not at this stage where we can have 3 billion devices running Pyodide, but we try our best. We are trying our best to make it run cross-platform. So this is a small meme on this. That if you had, we would be living in a utopian society if Python were on the same level as Java. So so this slide is based on Rust, Python, and Pyodide. So here, this is that I want to say that Rust, Python, and Pyodide both are offering a different implementation of the Python programming language that can run inside a WebAssembly runtime, because Rust can compile to WebAssembly, but Pyodide has this. Like it has this feature where you can run C Python extension modules. So for example, projects that use compiled code, for example, let's say NumPy, you can run NumPy inside Pyodide, but that use case is limited inside Rust Python. So it's more than just Python and WebAssembly. That's what I'm trying to emphasize, and that is that Pyodide is essentially Python, C Python. It has a very strong foreign function interface for exchanging data types between JavaScript and Python, with some associated glue code that is provided by the Emscripten toolchain, which is where you get WebAssembly code and a standard library that you can use from JavaScript. And then you also have your favorite scientific Python packages: NumPy, SciPy, scikit-learn, Pandas, Matplotlib, and many others. So we have 225 packages being compiled for Pyodide and essential low-level libraries that are currently available in Pyodide. And you can, just like pip, you can use micropip to install these inside the web browser or in a JavaScript runtime. And then all of these packages are available as wheels, similar to how you have wheels for regular platforms. So you can get them from the JS Deliver CDN. And if you have a pure Python package, then you can get them directly from PyPI. So let's switch to a demo, because yes, Pygame C, which is Pygame Community Edition, and HDL2, which is the simple direct media layer library. They also work since version 0.26. So I have a very small game to show you. It's Sudoku, because I like playing this game. So essentially, we can play this game and just like you would play it anywhere else in an Android app or somewhere. But it's running inside a browser tab, and it doesn't need any installation or any other resources besides an internet connection. So I can just complete one of the rows for the game. So if I were to type 1, this would not be correct because I already have 1. And this should be 3. And similarly, you can play this game. It's not completely ready yet. Like it's not completely bug free, but my emphasis is on the fact that you can create games using Pygame and then run them inside the web browser. So getting back to our presentation, so like I'll try to emphasize on the motivation behind all this. And the motivation is that scientific Python projects and developer environments associated with them, especially in the artificial intelligence and data science ecosystems, they're tricky and to install and manage. Essentially, that's why Conda exists, and that's why log files exist. So for maintainers and core developers of scientific Python packages, it's difficult to target various platforms and architectures. I'm not suggesting that you were to add another architecture to your list of already supported architectures, but what I want to say is that there is sometimes this steep learning curve to managing Python environments is sometimes a euphemism for asking people to do it themselves and not having clear documentation around Python packaging in general. So another piece of motivation is that having Python inside a web browser where you don't need to install anything, it lowers the barrier to entry for learning Python. So it has a lot of use cases in education for new programmers. So to this like emphasize on this point, there's this comic by XKCD where someone has a lot of Python environments on their machine, and it's difficult to manage all of them because, well, you have ultimately you have so many, and then it's difficult for you to uh, like have the right amount of developer experience for you. So as for other parts of the motivation, which is something that I'll come to later in my talk, it's that documentation for scientific software, especially in the Python ecosystem, needs to do more. And there are some guidelines on what such software should do, which is that it should be explanatory, should be illustrative, and also interactive. And I'll stress on interactive because Pydight is going to be like I'm just going to display an example on interactive documentation with Pydight. So this is a small pictorial representation of the diet access model for documentation for any piece of software in general. And what I like here are we'll stress on the understanding part here, on the understanding and explanation section. So as for literate programming environments in Python, where you have some bunch of Markdown, and then you have some bunch of Python code, and then Markdown, and so on, you have a lot of options for you: Google Colab, Binder, Jupyter Lab. You can run Jupyter Notebook locally and more. But there's also a new entrant, which is called Jupyter Lite. It's not really new, but it's like gaining popularity since the past few years, which is that it provides an implementation of Jupyter that runs natively inside the browser, powered by WebAssembly and Pydight. So essentially on Google Colab, you're running code on the server and you're receiving an output. So all of the code is being executed on the server. But in the case of Jupyter Lite, you have client-side execution. So all of the code is running on your CPU and your hardware. So essentially, that's like it helps you reduce your server costs if you're interested in that. So with Pydight, there are also a lot of limitations. So for example, some modules from the Python standard library are not available. So threading or multiprocessing are not available. So if you were to type out import threading or import multiprocessing, they would work, but none of the functionality works. And it would raise an error, a runtime error if you were to try. And the socket library from the standard socket module from the standard library does not work either. And then there are some restrictions on what you can run inside the browser. So here the browser is a runtime, and a browser cannot replace an operating system. And what I mean by this is that For example, having access to peripherals is like restricted. You can't run, you can't access the file system directly from the browser. Like you can't do it very easily. And also using multiple threads is limited to web workers and the like. So the browser is essentially like one of the most secure pieces of software in your computer, because all of these processes inside a browser in one tab are restricted. You have just one process for one tab, uh, and essentially you have boundaries across these tabs, so you can't share memory across these processes. So let's pivot to the next part of our presentation, which is the pyridite at the heart of scientific Python. So we have a bunch of scientific Python packages here. Um, let's do a quick show of hands. How many of you have used 5 of these? At least 5 of these? Okay. And 3 of these? Okay, some more hands. And at least one of these? Yeah, so I guess like most of the people here have used at least one of these, which means that like these are essentially uh, fundamental pieces of software that you can't really ignore if you use Python. So with this, we get to another part about pyridite's limitations. So about bitness, we have 32-bit memory addresses and 4 gigabytes of usable memory, and this is even less inside one particular tab. So you, for example, you might have not more than 300 megabytes of memory for a Chrome tab, and then there's no support for floating point exceptions. So, for example, if you were to divide something by 0, you would get a zero division error or some sort of different error that's not available here. So that's a limitation. That's not something due to pyridite, but due to WebAssembly in general. And then also Emscripten as a compiler toolchain also has an API. So whenever we update something, whenever we update Emscripten, we change the API, which means that we need to compile all the packages, the 225 packages that I displayed once again. And then you would have troubles with, for example, compiling one package, a particular package and all, and so on. So like, as for extending support for a new platform for like not just WebAssembly, but anything in general, you would need to fix compilation errors first, fix crashes and fatal errors, then organize a CI job so that once you have fixed everything, nothing breaks. And then this is all quite straightforward, if you wanted to say it, but it's also very complex to do. It's like you know all the steps, but you don't really know how to do each part of those steps. So here we come to another section of my talk, which is about the pyridite build system, because this is essentially what helps you compile to a new a new WebAssembly target. So the structure of a pyridite CI job would be that you would check out the repository, you would set up Python and Emscripten, invoke pyridite build to build wheels for your packages, install Node.js to run pyridite, run tests, and then you would have a successful CI job if everything worked correctly. So pyridite build will build your package outside of the tree, which means that it's going to build outside the pyridite repository as opposed to in tree. And then you can run test suits for your package using PyTest, just like you would do it for a regular Python package. So as for the pyridite build tool, it's a standards compliant distribution builder, which here standards compliant means that it adheres to the Python enhancement proposals around Python packaging, the PEPs, and the pyridite build wheel command builds the wheel. For pure Python packages, it's the same as a regular wheel. And then we have some special utilities to set up cross build environments. And we manipulate some of Python's data to trick the compiler into thinking that we are cross compiling. So this works very nicely with all build backends. So for all build backends that are used for compiled code, and CI build wheel, which is a tool for building platform-specific wheels. It also gained support for Pydite this year. And Emscripten is what is providing all of these replacements for, well, traditional compilers and build tools like CMake. So as for Pydite wheels, this is how a wheel is generally like the file name for a wheel is labeled. So pure Python packages are named in the same way, but compiled wheels get an Emscripten platform tag and also an ABI tag sorry, an Emscripten ABI tag and WebAssembly platform tag. So we have changed this now. It reflects Pydite instead of Emscripten, so that we can emphasize that this is a Pydite wheel and not an Emscripten wheel. So Pydite wheels will contain like code that is being compiled with the Emscripten toolchain. So for example, if we look at a SciPy wheel, uh, so you'll get a Linux binary here and an Emscripten binary. And the way you would uh, distinguish between both of these is through their magic number, which is that ELF binaries and WebAssembly binaries have a different magic number. So there have been some problems with my work towards uh, building all of these wheels for a lot of scientific Python packages this year. So one of the problems comes from Fortran. So Fortran is like, it's difficult to compile Fortran to WebAssembly without hacks. And to build SciPy, which uses a lot of Fortran, you need to use F2C, which is a tool to convert all Fortran code to C code and then compile all the C code to Emscripten, with Emscripten to WebAssembly. And this means that you need to patch a lot of things because, well, it's like, well, it's difficult because SciPy has a lot of Fortran code and for performance reasons, and Fortran isn't well supported. So one of the problems here is function signature mismatches, uh, which is like they're caused by either bad Fortran code, F2C bugs, or many other reasons. And why this is a problem is that WebAssembly is running inside a browser, and something that would raise a warning at compile time is now going to raise an error here at runtime, which means that like you could escape a lot of these problems when you're running a traditional, like if you're running things on a Linux or macOS machine or a Windows machine, but that's not the case for a web browser. So these errors look like these, where a function pointer points to two inputs, and the symbol for the function asks for three inputs, and so on. So let's come to almost the end of our talk, which is about interactive documentation. Like a lot of these problems will be hopefully resolved sometime soon. As for interactive programming, we're all aware about its benefits. Immediate feedback loops, you can use it for learning and experimentation. It improves learning experience for users and all. So with one thing that we have done over through this year is that the NumPy and SciPy docs are now interactive. So they're not completely ready yet, so they are disabled, but you can run them if you want to. So I'll show this example from uh, the NumPy documentation. It's on my fork. It's in a PR that has not been merged yet. This is an example of the NumPy fast Fourier transform page, where you can go to the end of the page and look at the examples, conduct a fast Fourier transform using NumPy's API. So just clicking on this button, try it in your browser, opens up a small notebook for you right inside your browser's tab, which is going to use Pydite. So now if we were to run this, it should all work. Maybe it won't because I'm not sure how well the internet connection here is. So we can wait for, let's say, 15 to 20 seconds and see if it works. And I also opened the console so that you can see that all of the packages are being downloaded for you right inside the browser environment. And yeah, so it works. We have an array, and we also have a plot. So you can also use matplotlib inside the web browser. So let's come back to our presentation. So how this is all working is Jupyter Sphinx. Jupyter Sphinx is a Sphinx extension that combines Jupyter Lite that I previously showed with Sphinx for your documentation websites. So you can convert all of the examples in your documentation to notebooks. And then Jupyter Lite is essentially what provides the runtime for you for running those examples. So you can just add this stub to your docstring, and you will be able to have a button like this for your packages documentation if you use Sphinx, that is. So you just need two packages for this, Jupyter Sphinx and Jupyter Pycon kernel. And there are other kernels available as well. So we've already seen this example. So there are many other things that we want to do. One is that you might have seen that the example took some while to load, which is because, well, we had to download a lot of packages, some essential packages, then NumPy, and then so many more packages. So we want to make those smaller. Like we can just like shred a few megabytes. That's very helpful because like all of this is not persistent. Preserving bandwidth. And then we would like to do this for more scientific Python projects. So with this, I would also like to conclude my presentation. We've had a new release very recently, just last week. And like we would like to proceed with more improvements wherever we can. So this is a small section on some Pycon projects, some projects that are already using Pycon. So I'm not sure if we have enough time to go through all of them, but you could take a picture if you want to, or talk to me later. And we have some more projects on the Pycon website. This is a small graph of what I explained during my presentation about how it all works and how the ecosystem is like essentially powered by all of these things work together. So we have learned a lot of things about Pycon today, and also about interactive documentation. And there's a lot of ongoing work to improve both the build system and the scientific Python ecosystem in Pycon. So if you're interested, you help maintain Pycon. So if you're interested, you can, if you want to add your package to our repository, you can do that. You can open an issue or a PR to do it. And that's it. Thanks for your time. Here are my socials and my email address and some QR codes for the slides and the Pycon repository.
Thank you so much for the inspiring presentation. Thank you so much. And this concludes our session for this session. We hope you find it insightful, and see you again in the next session. Thank you, everyone.
Do we have time for questions?
Actually, the
No?
time is already up, but
Okay.
there's like a 15 minutes break. So
Yeah.
if anyone wants to have any questions, go ahead.
For the game? Sure. Do you mean this one? I can show it again if you want. Sure. So like if we were to modify any of this, we should get a different array. And if we were to change some of the things here, maybe you would get a different plot and all. Yeah, it's inside your browser, and all of it runs inside. It runs with your own CPU, so it's not running from a server or anywhere. This is the Arc browser. It's a Chromium derivative. Yeah, all major browsers from Safari to Firefox to Chrome, all of them work. Not really. If you have a website that has Pydight code within it, you don't need to install anything. But if you meant if you meant interactive documentation, then yes, you need a Sphinx extension for it. It's called Jupyter Light Sphinx. It's a Sphinx extension that uses Jupyter Light to render notebooks inside your terminal. And here's the documentation for it, if you would like to see it.
So can we using this as a web scraper?
You could, but then you could also run into errors such as coarse errors, because you're retrieving data from another source, and then
And the headers will be the browser headers, or we need to set up the headers also.
I think you would need a proxy. Yeah,
Ah,
yeah. So if you already have coarse headers, you don't need it. But if you want them, then you need to set up a proxy. Yeah.
but we cannot fit the LLM model.
You could do that. We have some limited use cases. The issue is that, for example, um, so like because we don't have sockets or threading and many of those things, running things like the standard library, the Python standard library is limited. So if you want, like for example, requests is now supported, but it took a lot of work to get that done, because it's an entirely different environment. It's not like a regular Docker container, but it's inside a web browser. So yeah. Okay, I guess no more questions.